Good morning, guys.
Morning.
Got lots of work, lots of mixing. Oh yeah. What are we mixing, Corbin?
We are mixing some 110 right now.
110. So we got a bunch of various materials to mix. This is about half. We had a bunch of it yesterday. Look at all that. We'll get it. We'll get it all done. Let's see how full the dryer is. Oh yeah. Yeah, I would say there's quite a bit of work in there. There's some older stuff. See what Tom's got going on. Oh, finally got you a fan. It's hot over here, isn't it? He's running plates in this bad aspiration box. You crush the cubes as well? And he only got you a couple sets? Yeah, there's that worm dirt again. Can't hear what he's saying. All right, so I'm getting a lot of questions about API, the testing as far as the lab is concerned, the lab portion of the API test. So I decided I'm going to go ahead and put some of this in a video for anybody who's wanting to know. I mean, if you have a lot of money, you can take the class that Tony Sims offers, but for the rest of us broke asses, this is the best I can do for us. So one of the things you're going to want to remember is the ASTM testing codes. For this case, the cold crushing strength is the C133. And this little chart down here looks very confusing. But all that's what it's saying is, first one there, if your density of your material is greater than 100 pounds per cubic foot, then you're going to crush it at 2,500 psi a minute. Your density anywhere between 60 to 100 is going to be crushed at 300 psi per minute. Less than 60, you're going to go at 250. Now, here's a little trick. The very last portion of this, right, says 50% of the anticipated load may be applied at any convenient rate. So, for instance, if your material is going to end up crushing at a total of 5,000 psi, you can run it up to 2,500 psi at any rate you want. After that, you're supposed to be following this chart. So you might want to go ahead and stop now and take a screenshot of this just so you have it, so you can remember, because these are very tricky questions. One more thing, cold crushing, is that this here, this round spherical, see this sphere here, move this cube. This is a spherical bearing block. The reason it's a spherical is because it's round, right? Circular. So this and this are the spherical bearing blocks. It's always easier to put your eyes on it than it is to read a book about a spherical bearing block and not knowing what the hell it is. Let's see, another test question they have here is for the shims. The shims, open that back up, Tom. So you can see on his cube here, he has these brown shims on top and bottom. So here and here, in between the spherical bearing blocks. Can you put that out for me? Those shims look like this. Okay, they're non-corrugated, which means there's no corrugations in there. Like this one. So this is a piece I cut out of a box. You can see that this one is corrugated. See all the corrugations that are in there? So they want you to use non-corrugated. So no corrugation. Solid cardboard, or they give you like an 1/8 inch paper type of shim. We always use these just because they give us better numbers, more consistent numbers than those paper shims do. So remember that. Corrugated, non-corrugated for cold crushing strength, which again is the ASTM C133. All right, so for the ASTM C704, it's abrasion resistance test. Those codes are very important. So this is kind of a copy of the procedure of what we're doing. I have one of these on every wall for every area that we work in. So let's just run right through all this mumbo jumbo. This is a lot of just ununderstandable crap. So let me run you through that. So we're going to use 1,000 grams of silicon carbide. That's what it looks like. It looks like black sand. All right, so we put that on the scale. Come on. Scale's at 0. Zero out your deal. Dump your sand in there. Let's see what we got. 1,000 grams plus or minus 0.5. I don't like to do that. So we're going to get just a little bit more here out of the barrel and get that right. Oop, a little bit much. You want to go plus or minus, you can go plus or minus 0.5 grams. That's your tolerance for the test. That is one of the questions. So we're going to want to remember that. All right. So inside here, this is a calibration rod. It is calibrated exactly at 8 inches. So once your specimen is inside, your tolerance for this is 8 inches between the plate and this tube. All right. So clearly this one would need to be adjusted up a little bit, but that's fine. You have a tolerance of like an 1/8 inch or so. And then the plate that is abraded, the surface of it, which you can't really see on that specimen because it's white. So you can see here on the back side where this was the mold bottom or the mold side. Then on top, you can see where it's been cut. So it's this direction because this is the most representative of the hot face. That's another test question. So it needs to go into the machine with the hot face facing up and not the other way. Doing it this way will give a false reading, a false number. Another thing, let's see. These are pieces of glass that are in this sleeve here. It's called flint glass tubing. So this is what a new one looks like. Nice and pretty. This is 7mm ID flint glass tubing. Now, just like the silicon carbide, this tube can only be used once. So as you can see, this one was just finished doing an abrasion test, so that's going to get pulled out of there, and this new one's going to get put in there. So 7mm flint glass tubing. So 8 inches from the specimen to the bottom of this tube is the correct measurement for C704, not to be confused with any other measurements, because 8 inches is very, very close to another measurement that we use in here. So remember, 8 inches is for abrasion resistance. So then we move on to the PSI. Now, the correct answer for that is 65 PSI. But in reality, it doesn't really matter as long as we're in calibration from 9.1 to 9.5. See our glass plates here. It says 9.3. What does this one say? It didn't actually say anything. Oh, 9.8. That one didn't make it. So it doesn't really matter the pressure. But on the multiple choice questions, the 65 PSI is the correct answer for that. Moving on to the timers. This is something you're going to have to remember because this test is timed. This is a little timer. It drops the silicon carbide into this funnel within a certain amount of time. So if you go back to our board, our range there is 7:15, 7 minutes 45 seconds. So you have a 30-second plus or minus variation for that. That is definitely a test question. It could be another test question. It could be how do you report your loss, and that's in cc's, which is cubic centimeters. Back in the old days, it used to be millimeters, which is the same exact thing as a cubic centimeter. But that's how you report, is in cc loss. So cubic centimeters. Okay, just recap. Remember, 8 inches for abrasion resistance test. 1,000 grams of silicon carbide plus or minus 0.5 grams. 7 minutes to 7:45 minutes is the time the test can run. 65 PSI on your pressure. They shouldn't be asking about Venturi nozzles or any of that trash, but you never know. They always ask some outdated questions. Okay, the ASTM C134 for bulk density. Again, there's just our chart with a bunch of mumbo jumbo on it. But you can screenshot that if you want to read through it and kind of follow along with what I'm going to say over here, because it can get a little tricky. All right, Nathan, I'm going to need your spot. So what that's saying over there is that you're going to do everything to your nearest, watch your decimals on that. So when you're studying for this, make sure you pay attention to your decimals. Sometimes there's 2 zeros behind the decimal. Sometimes there's only one. Be sure to watch that decimal, because those are test questions. And so what we're going to do for this is we're going to measure, sorry, getting a phone call. We're going to measure this cube from 3 different sides. So that's 1, that would be 2, this would be 3, right? We're gonna hit those down in our inches. Then it comes over to the scale, and this is where your decimals come in. So we have, turn that fan off. The scales are very, very sensitive in here, so the scales sometimes affect things. So we got 167.1. So that's your decimal that you have to remember. If we're reading through the spec, you're reading that board over there, it'll tell you to the nearest 0.00 or 0.01 gram. That's what this is in. Come on, light back up. Come on. And that was in grams, as you can see. And that's pretty much it for density. I mean, you have to have your little apparatus calibrated, zeroed out. The scale needs to be zeroed out, and it needs to be third-party calibrated annually. That's pretty simple. So that was the C134 for density, and then we can move on to the C113, which is the permanent linear change. So this one is a lot easier than how it reads. Yeah, give me that. Yeah, give me one of those that actually look worth the shit. So I'm gonna get that in there. Okay, we're gonna put a bar, our 9-inch, 2-inch by 2-inch by 9-inch. That's another thing. I keep paying attention to your specimen sizes. So the cubes were 2 by 2 by 2. This is 2 by 2 by 9. So we're gonna put this in here, and it's gonna give us a measurement. Let's say this is green, which means it hasn't seen any temperature yet. This will then go into our dryer for a specified amount of time, whether it's API, ASTM, or all them other ones that want to jump in there with an hour less than the other one. So once it's at 230 degrees for a specified amount of time, we'll bring it back over here, put it in again, and it's going to lose a little bit depending on its density and depending on what it's made for. Then it's going to go into our kiln. We're going to fire that to 1500 degrees for 5 hours, and then we're going to measure it again. And so this is going to be 0.000 on your decimal. So for permanent linear change, there's 4 numbers. 1.000. So just think of it as 4 zeros with your decimal after the first 0. It sounds complicated, but once you do it in your head 1,000 times, it's pretty easy. Okay, so this one, let me get that glare out there for you. So this one is the permanent linear change, which is the C113. It has all your specimen sizes in it. So you see right there the 0.00 inch. There's your 4 numbers I was talking about. It's easier to see it. It really is than to just read it in a book somewhere. So that's what we're trying to do, is try to make it a little easier so everybody will stop calling and asking questions, which I don't mind doing. I love to help, but when I get 30 people a day trying to ask questions, the same ones over and over, it's just easier for me to make a video and everybody watch the video so you can go back and rewatch, take screenshots of these things, whatever you need. That's what. All right, another section, another complicated looking chart. And I think in the 5th edition, this is not table 4 anymore. I'll have to look and see exactly what table this is. But this is for brick saw cutting. And it is, so this is the, one of the questions is the minimum number for erosion service. As you can see here, that's going to be 3. That's your minimum count. So you need 2 plates and 1 PLC bar. So these are your specimen measurements. 4.5 inches by 4.5 inches by 1 inches is the abrasion plate size. The 2-inch by 2-inch by 9-inch is the PLC bar, as we call it. And so the answer to that question is 3. And then, of course, over here for other services, which is just non-erosion, or in reality it's called abrasion, you just need 3 cubes, 1 bar, and again your sizes. So if you need to take density from anything else, you can always take density from the cubes or the PLC bar itself. Sorry, there's a bunch of refractory all over this. We are in the shed where we use our 20-inch brick saw. Let's see. That could be a good screenshot there for you. All right, for mixing, ASTM 862. So we're preparing specimens by casting. Again, this one's not really all that mumbo jumbo. This one is a lot of good information here. So the conditions to be 70 to 80 degrees, 40 to 60% humidity. You got to use scales. You got to batch out stuff. Use clean water, potable water. And they say a paraffin or silicone base. We normally use WD-40, but there's sometimes people want us to use olive oil or some kind of organic whatever. And then, of course, you're going to leave your specimens in its molds with either curing compound, or in the lab we use a plastic trash bag, a sheet, a roll of plastic, and we allow it to cure for 24 hours. So just maintain your temperatures, and you can do that by controlling your material temperature and your water temperature. There's not always much we can do about that humidity, especially out in the field, or even in the lab. This is not an air-conditioned facility. This is just a warehouse, And so they want to jump on us about that, they can, but most of the time they don't. But if it is one of the questions, so let's keep that in mind. Okay, I'm trying to climb through all this shit. Okay. This is the ASTM 865. This is for firing in the kiln. And so this is where it gets a little tricky, because they want you to know all these weird numbers per hour and holds and all this shit. You just got to remember that 300 degrees an hour is at its top level. It's the most aggressive firing. That's as most as you can do in an hour is 300 degrees. All this other stuff up here, that's just something that we do here at the shop, in the lab, to ensure that we don't have any spalling. But all this, it's rolled up into, it's going to go 300 degrees an hour until it hits 1500 degrees, and then we're going to hold there for 5 hours. That's a test question. The other test question they have for this is going to be the cool down rate. And as you can see right here, it's at 500 degrees an hour to ambient. That's the standard ASTM API. But again, we just do extra here. So all that other stuff is just what we do here. All right. Hey, I'm going to need you to take density from those bars.
All right.
As well as the cubes, but I want
Both density?
Yeah, I want both of them on that one, please.
All right.
We'll go check on Tom, see how he's doing. How you doing, Tom? Good?
Oh yeah.
This guy. Sometimes you can't hear me. Hey, before you get started. Let's see how they look. They look pretty good? Yeah, they do. Okay.